Tonight, we're taking a journey, a quiet trip far from our own familiar solar system. We're going to explore some of the most fascinating and sometimes unbelievable facts about other planets. Worlds beyond our sun that spin silently in the vastness. It's a chance to just let your mind wander a bit, to think about the incredible things that exist out there, far beyond what we can easily see. So, get comfortable. Just let your body relax, and let's begin our exploration of these distant, mysterious places. You know, some planets out there get hotter than stars themselves. We usually think of stars as these incredibly hot, glowing balls of plasma, burning at millions of degrees. But there are actually a few planets that come pretty close to that kind of intense heat. Imagine a world like Kelt 9b. It's a gas giant much larger than Jupiter, and its surface temperatures can soar past 7,000 degrees Fahrenheit. That's significantly hotter than the surface of many red dwarf stars, which are common across our galaxy. The main reason for this extreme heat is how incredibly close it orbits its parent star. Kelt 9b circles a massive, intensely bright blue star. This star is huge, much bigger and hotter than our own sun, and it bathes the planet in a constant, brutal barrage of radiation. The planet's orbit around this star is incredibly fast. It completes a full revolution in just a little over a single Earth day. Think about that for a second. Its year is shorter than our day. This close proximity also means Kelt 9b is tidally locked. That's similar to how our moon always shows us the same face. On Kelt 9b, one side of the planet is perpetually facing its star, locked in an unending, scorching daylight. The other side is trapped in eternal darkness, though it's still incredibly hot due to atmospheric circulation. The constant, intense radiation from the star is literally stripping away the planet's atmosphere. We've observed it streaming into space, forming a long, wispy trail of gas, almost like a massive, dissolving cloud. This process means the planet is slowly, gradually losing its outer layers, evaporating bit by bit into the void. The heat is so unbelievably intense on Kelt 9b that not only do molecules struggle to stay together, but even metals, like iron and titanium, can vaporize. They don't just melt, they turn into gas, floating in the planet's upper atmosphere. It's an environment that's just beyond our normal comprehension of planetary conditions. These kinds of planets, often called ultra-hot Jupiters, really push the boundaries of what we thought a planet could be. They make us question the clear distinction between a planet and a small, failed star. These are blazing, turbulent worlds, constantly being battered by their stars, and their existence might actually be quite fleeting. They might only last for a relatively short cosmic period, before they entirely dissolve into the surrounding darkness, leaving behind perhaps a much smaller, denser core, or simply dissipating completely. It's a dramatic, intense scene playing out light years away. Now, shifting gears a bit, some planets could be made almost entirely out of diamond. That sounds like something straight out of a science fiction movie, right? But under specific conditions, it's a very real possibility in space. Imagine certain exoplanets, especially those that are particularly rich in carbon. They might form in a way that leads them to be composed mostly of solid diamond. This happens if a planet develops around a star that has a higher proportion of carbon compared to oxygen. The raw materials available during the planet's initial formation would then be carbon dominant, leading to structures that are rich in this element. One very strong candidate for this kind of world is 55 Cancri e. This planet is often referred to as a super-Earth because it's roughly twice the size of our own planet. Scientists believe it might contain an absolutely enormous amount of carbon deep within its interior. And here's the key. The immense pressure found deep inside a planet's core can transform carbon into its crystalline diamond form. So rather than having a rocky mantle like Earth, 55 Cancri might have vast, deep regions of pure, solid diamond. It wouldn't necessarily sparkle or glitter like a cut gem in a jewelry store. We're talking about diamond on a planetary scale, which, in its raw, unpolished state, and under such extreme pressure and heat, would likely appear dark, incredibly dense, and unimaginably hard. There wouldn't be anything here for a jeweler, just raw, dark, compressed carbon. Still, the sheer idea is truly captivating. A world that was forged primarily from carbon, where the very mountains or geological structures deep inside could be composed of buried crystal. It's a place where the geology is elevated to something almost fantastical, something incredibly precious, and unlike anything we experience on our home world. It truly broadens our understanding of the different compositions planets can have, moving far beyond the familiar rock and iron cores we know. Moving on, some exoplanets actually orbit two suns, much like the famous depiction in Star Wars of Tatooine. For a long time, the idea of witnessing two sunsets, with a pair of stars slowly dipping below a distant horizon, was pure fantasy. But now, we have definitive proof that these kinds of strange, double-starred skies can exist. There are indeed exoplanets that don't just circle a single star, like Earth does with our Sun. Instead, they orbit two stars that themselves are locked in a gravitational dance. These are known as circumbinary planets. They trace beautiful, often complex paths around their stellar pair. When these two stars are situated very close to each other, a planet can actually orbit both of them, as if the pair were a single, larger gravitational body. It's like a cosmic ballet, where the planet gracefully sweeps around the duo. However, if the stars are farther apart, the planet might orbit just one of them. But its path would still be significantly influenced, tugged and tilted by the distant gravitational pull of the second star. The outcome of such an arrangement is a world that experiences incredibly unusual light cycles. Imagine days with two dawns and two dusks, or perhaps periods where one sun is always visible while the other comes and goes. The seasons would be much more dynamic and complex, shifting with the relative positions of both stars. And, of course, there would be double shadows, creating intricate patterns across the landscape. These kinds of systems are considered quite rare, and their delicate gravitational balance makes them somewhat fragile. Yet, they are absolutely real. So, the sky above some far-off world truly might glow with not one, but two rising suns, and then later, two setting suns. A celestial view once thought to exist only in our imaginations has now been quietly confirmed by scientific observation, showing us the incredible diversity of star systems. Some planets, incredibly, experience rain made of molten glass. When we think of alien worlds, even our wildest imaginings often fall short of the reality. Consider a gas giant known as HD 189733b. This planet is larger than Jupiter and orbits so incredibly close to its star that it completes one full revolution in a little over 2 Earth days. Its atmosphere is absolutely scorching, with temperatures reaching around 700 degrees Fahrenheit. The winds on this world are ferocious, whipping around at thousands of miles per hour, creating an incredibly turbulent environment. Suspended within its hazy, deep blue skies are tiny, microscopic particles of silicates. Silicates are the fundamental building blocks of glass here on Earth. Under the extreme heat and pressure of HD 189733b's atmosphere, these silicate particles can condense. When conditions are just right, they don't fall as water or ice, but as molten glass. And because of those incredibly powerful, high-speed winds, this molten glass rain isn't falling straight down, it's swept sideways, creating horizontal sheets of liquid glass. From a great distance, this planet actually looks quite beautiful, almost deceptively Earth-like in its color. It displays a soft, shimmering blue glow as it orbits near its star. But if you were to somehow get closer, you'd find a storm-racked furnace, a place of violent beauty, completely uninhabitable by any life we know. It's a vivid reminder that the universe's imagination for creating unique, extreme environments far surpasses our own. These kinds of exoplanets really highlight how diverse and sometimes utterly hostile planetary weather can be. There are other planets that might be entirely covered in oceans thousands of miles deep. Imagine exoplanets that are essentially ocean worlds, almost completely swathed in water. Picture no continents, no islands, nothing but a seemingly endless global sea stretching across the entire surface. These aren't like Earth's oceans, which only reach depths of a few miles at their deepest points. On these distant worlds, the liquid layer could be hundreds, or even thousands of miles thick. At the very surface, the water might appear calm, stirred by gentle winds, or perhaps raging with immense storms, depending on the planet's atmospheric conditions. But as you descend deeper and deeper, the pressure would steadily increase to absolutely incredible extremes. This crushing weight can lead to the formation of exotic types of ice. We're not talking about the familiar ice we know, which floats and melts easily. This is dense, high-pressure ice, forms that can only exist under such immense gravitational forces. It behaves more like rock than frozen water. These planets would likely still possess rocky cores at their very centers, but they would be hidden far beneath these colossal water layers. Some of these ocean worlds might even have liquid layers deep down that are kept warm by internal geological heat, perhaps from radioactive decay or residual heat from their formation. The possibility of life existing in such deep, dark and high-pressure oceans is a profound question. We don't yet have an answer, but it's thought that ocean worlds might be much more common than we initially imagined. They are gentle, glistening planets, with no visible landmasses, quietly turning in the vast darkness, far from any star we recognize, yet potentially holding secrets of their own. Some planets are tidally locked, meaning one side permanently faces their star. Not every planet spins on its axis in the same way Earth does. Some are caught in a phenomenon called tidal locking. This means that one hemisphere of the planet is always, perpetually, facing its star, while the other side remains in unending darkness. We see a similar effect with our own moon. We only ever observe one face of it as it orbits Earth. But try to imagine this on a planetary scale. You'd have one hemisphere that's relentlessly scorched by continuous daylight, never experiencing a sunset or a night. Conversely, the other hemisphere would be trapped in eternal night, a cold, dark realm that never sees the light of its sun. In between these two extreme regions, there would be a twilight zone. This is a narrow band, or ring, around the planet where the light is always low, a perpetual dusk or dawn. And in this particular zone, the temperatures might actually be just right, not too hot and not too cold, potentially allowing for liquid water to exist. Some scientists hypothesize that, in certain specific circumstances, life could possibly thrive and survive within this thin band of balance, adapting to the constant, subdued light. These tidally locked planets often experience fierce winds, driven by the extreme temperature differences between the day and night sides. They can also have strange, unique cloud formations and wildly extreme weather patterns. But they are absolutely real, and their existence truly challenges our preconceived notions of what makes a world habitable. Life, if it were to emerge on such a planet, might learn to flourish either in the deep shadows or right on the very edge of the continuous light, evolving in ways we can barely comprehend. Moving on, hot Jupiters are planets that skim so close to their stars that their atmospheres literally boil off. Try to picture a planet similar in size and composition to Jupiter. It's massive, primarily gaseous, and utterly immense. Now, imagine moving that giant world incredibly close to its star. So close, in fact, that a single orbit takes only a few Earth days. So close that the temperatures on its surface and in its atmosphere soar well beyond 2,000 degrees Fahrenheit. These are what astronomers call hot Jupiters. They are enormous gas giant planets that orbit incredibly near to the surface of their host stars. They're so close that their upper atmospheres are quite literally being blown away, evaporating into the surrounding space. We have actually discovered many of these peculiar worlds. In fact, hot Jupiters were often among the very first exoplanets that we ever detected. Their sheer size, combined with their extremely tight orbits, makes them relatively easier to spot using our current observational techniques. However, despite being easier to find, they remain profoundly mysterious. A big question for scientists is how such massive planets manage to get so incredibly close to their stars. Did they form in that extreme proximity? Or were they initially formed much farther out, and then gradually pushed inward over vast stretches of time by complex gravitational interactions? Some of these hot Jupiters leave glowing trails of gas behind them, much like comets, as their atmospheres continuously escape. Others are slowly but visibly shrinking as their gaseous envelopes evaporate into the stellar wind. They are inherently unstable, dramatic, and often quite short-lived in cosmic terms. They represent brief, fiery flashes of planetary existence, circling distant suns for a relatively short period before their eventual dissipation or transformation. They really show us the extreme dynamics that can occur in planetary systems. Interestingly, some exoplanets are actually darker than charcoal. Not all planets reflect light in the same way our bright blue Earth does. Some worlds absorb almost every bit of light that falls upon them, making them appear incredibly dark. Darker than black paint, darker than ash, even darker than charcoal itself. One such world is a gas giant known as Tres Tubi. It orbits a star located about 700 light-years away from us. Its atmosphere is so incredibly dark that it reflects less than 1% of the starlight that hits it. Scientists aren't entirely certain about the exact reasons for this extreme darkness. It's thought that it could be due to the presence of vaporized alkali metals, or perhaps some unknown chemical compounds existing in its upper atmospheric layers that are highly light absorbent. Whatever the precise cause, the result is truly extraordinary, a planet that is as black as coal, emitting only a faint glow of its own internal heat, making it almost invisible when trying to observe it by reflected starlight. Even the planet's night side, which is already in darkness, is only slightly cooler than its perpetually illuminated day side. If you could somehow stand nearby and gaze toward this world, you would likely see only the faintest silhouette outlined against the fiery brilliance of its host star. It's almost a perfect shadow, silently orbiting through space, relentlessly absorbing the light of the universe around it. These incredibly dark worlds truly challenge our assumptions about how planets interact with the light from their stars. And then we found planets that float completely alone, without any star at all. Most planets, as we know, are gravitationally bound to a star, orbiting it in a predictable path. But not all of them. Some are true wanderers, free floating planets that drift through the vast, empty stretches of interstellar space entirely on their own, unbound by the gravitational pull of any sun. These are commonly referred to as rogue planets, and we've gathered evidence suggesting the existence of dozens, possibly even hundreds, of them scattered across our galaxy. They might have formed in a typical planetary system, much like our own, but were then violently ejected from their home systems due to powerful gravitational disruptions. Perhaps a close encounter with another massive planet, or even a passing star, could have flung them out. Alternatively, some rogue planets might have formed in isolation, never quite gathering enough mass to ignite into a star, essentially becoming failed stars that wander alone. These worlds are inherently dark, incredibly cold, and consequently, extraordinarily difficult to detect. However, with the aid of powerful infrared telescopes, we can sometimes catch faint hints of their residual thermal glow, the leftover heat from their formation, or perhaps from internal radioactive decay. Some of these rogue planets might still retain enough internal heat to maintain subsurface oceans in a liquid state for billions of years, protected by thick icy shells. Others could be completely frozen solid, destined to drift forever through the absolute blackness of space. Imagine a planet that never experiences a sunrise, a world that has no sky in the traditional sense, just the endless, star-studded void. And yet, even in such profound stillness and isolation, a quiet and profound question lingers: could something, some form of life, possibly exist and thrive in such an environment? It's a truly humbling thought about the persistence of existence. Some worlds may literally have clouds made of rubies and sapphires. When we envision clouds, our minds typically conjure images of soft, pale, ever-shifting water vapor floating in Earth's sky. But on certain exoplanets, the atmosphere might shimmer with actual gems. On scorching hot gas giants, where temperatures can dramatically soar above 2,000 degrees Fahrenheit, minerals that would normally be solid rock on Earth can actually vaporize. They rise into the upper atmosphere as a gas, then cool and condense, forming clouds. These mineral clouds could be composed of substances like aluminum oxide, iron, or titanium. And in some extraordinary cases, they might even contain corundum, which is the mineral form of both rubies and sapphires. These gem-laden clouds would scatter light in very unusual ways, possibly tinting the planet's skies in vibrant shades of red, purple, or deep blue. On one specific planet, known as Westpoint Toy 1b, researchers have observed shifting patterns within its atmosphere that strongly suggest the presence of high-altitude mineral clouds sweeping across its sky. It's genuinely challenging to picture a world wrapped in such extreme heat and perpetual storms, illuminated by a blazing star, with clouds of what are essentially liquid or crystalline gems glinting and swirling directly overhead. It's a powerful illustration of just how much stranger and more beautiful the universe is than our limited imaginations can easily encompass. These worlds truly expand our sense of what's possible in celestial meteorology. There are super-Earths that might actually be more habitable than our own planet. some exoplanets fall into a category astronomers call super-Earths. These are rocky planets, larger in mass and size than Earth, but still smaller than gas giants like Neptune. Due to their greater mass, they might possess stronger gravity, which could help them retain thicker atmospheres. This, in turn, could potentially lead to more stable climates over long periods. And some of these super-Earths may actually be even more hospitable to the emergence and sustenance of life than our very own world. One promising candidate is Kepler 442b. This is a rocky planet situated squarely within the habitable zone of its star. This means it's not too hot and not too cold, receiving just the right amount of starlight to potentially allow for liquid water on its surface. Furthermore, its substantial mass suggests it has the necessary gravitational pull to hold onto a significant atmosphere and, crucially, to retain liquid water over billions of years. Some theories suggest that certain super-Earths could have deeper, more expansive oceans. They might also experience fewer tectonic disruptions, meaning less extreme geological activity like massive earthquakes or widespread volcanism. This could lead to greater surface stability, creating conditions that might be more favorable for life to emerge and endure over evolutionary timescales. Of course, at this point, we don't definitively know if any of these particular planets are truly habitable or if they harbor any form of life. However, they serve as a humbling reminder that Earth might not necessarily be the absolute, perfect planet for life. It's simply the unique world we happen to call home, and other variations could be equally, or even more, suitable for biology. We've observed planets that complete an orbit in just a few hours. Most planets take a considerable amount of time, typically months or even years, to complete a single journey around their star. Our Earth, for instance, takes one full year. Even Mercury, the fastest planet in our own solar system, still requires 88 Earth days for one orbit. However, some exoplanets move at an astonishingly faster pace. We've actually discovered worlds that race around their stars in a mere matter of hours. One of the quickest known examples is Kepler 778b, a planet that's only slightly larger than Earth. This particular world manages to complete a full orbit every 8.5 hours. Think about that, its year is less than half an Earth day. It's located so incredibly close to its star that its surface is almost certainly covered in molten rock, with temperatures reaching several thousand degrees. These ultra-short-period planets are often tidally locked, meaning their day and night sides are essentially frozen in place, never changing. From the surface of such a world, its star would loom enormous in the sky, dominating the view. The intense gravity from the star would exert powerful tidal forces on the planet's structure, constantly pulling and stretching it. Some of these planets may even be slowly tearing themselves apart due to these extreme forces. These worlds are undeniably extreme, incredibly fast, blisteringly hot, and likely quite fleeting in their existence. Yet they exist, skimming the very edges of their stars, like tiny sparks continuously flying from a colossal flame, demonstrating the sheer range of orbital mechanics possible. Conversely, other planets take centuries to complete just one orbit. While some exoplanets are racing around their stars in mere hours, others take a truly remarkable amount of time. Their journeys are long, silent, and can stretch on for many centuries. One of the slowest moving planets we've managed to find is Gu b, which is a gas giant. This colossal world takes approximately 1,000 Earth years to complete a single orbit around its star. Its orbit is so incredibly distant that it's barely held by the star's gravity. If it were even slightly farther out, it might break free entirely and become a rogue planet, drifting alone. These long-period planets are notoriously difficult to detect precisely because of their slow, extended orbits. We can't simply wait 1,000 years to observe them complete a full loop. Instead, we catch them in motion, noticing a subtle curved path, a long, gradual arc against the background stars, which offers a hint of something vast and distant. Some of these planets would have intensely cold, dark surfaces, illuminated only very faintly by the distant starlight from their sun. Others might experience seasons that last for multiple human lifetimes. On such worlds, the very concept of change would be measured not in our familiar years, but in generations. It would be a slow and silent rhythm, operating on a timescale far beyond our own everyday experience. These planets offer a profound sense of cosmic patience and endurance, quietly tracing their immense paths through the dark. We've discovered thousands of planets beyond our solar system. For the vast majority of human history, our understanding of planetary systems was limited to just one, our own. We knew of our sun, our moon, and the few wandering stars, which we now know are planets that moved across our night sky. But everything dramatically changed in the 1990s, when the first exoplanets, planets orbiting other stars, were definitively confirmed. Now, thanks to dedicated space telescopes like Kepler and TESS, we have found thousands upon thousands of these distant worlds around other suns. These discoveries include a huge variety of planets. Some are small, rocky, and potentially Earth-like. Others are massive and incredibly strange gas giants. Some hug their stars so tightly that they complete an orbit in just a few days. Others embark on journeys that take centuries to complete a single trip around their star. Each new discovery consistently reshapes what we thought was even remotely possible in terms of planetary formation and evolution. And remarkably, this is still just the very beginning of our exploration. Astronomers believe that there are hundreds of billions of planets within our Milky Way galaxy alone. That's potentially more planets than there are stars. Imagine that, worlds upon worlds, quietly orbiting in the vast darkness. While we'll likely never physically reach most of them, we can listen for them, measure the subtle shadows they cast, and continue to wonder what other incredible things might be waiting out there, circling in the quiet. We've detected planets by observing the shadows they cast during transits. The light emitted by a star is typically quite steady and constant. However, sometimes for just a brief period, that light will dim ever so slightly. It's a tiny dip, a momentary flicker in its brightness. This subtle dimming can be a clear indication that a planet has passed directly in front of its star from our vantage point. This observational technique is known as the transit method, and it has become one of the most powerful tools we possess for finding exoplanets. When a distant planet crosses the face of its star, as seen from Earth, it casts a faint shadow. This isn't a dramatic, total eclipse like we sometimes see with our moon. Instead, it's a very subtle drop in the star's overall brightness, often less than 1%. Space telescopes, such as Kepler and TESS, have masterfully used this technique to identify thousands of exoplanets. From just these minuscule shadows, we can glean a surprising amount of information. We can determine the planet's size relative to its star, the duration of its orbit, and sometimes even get hints about the composition of its atmosphere by analyzing how different wavelengths of light are absorbed. Essentially, we are watching distant stars blink ever so slightly to learn about unseen worlds. It's like deciphering a secret message in the light. A message that tells us about the quiet silhouette of a planet passing far away, briefly interrupting the steady glow of its distant sun. Other planets were discovered by the gravitational wobble they cause in their stars. Even the gravitational pull of a planet, no matter how small, leaves a detectable fingerprint on its host star. When a planet orbits a star, it's not just the planet that moves. The star itself also experiences a tiny, reciprocal tug. This causes the star to wobble, ever so slightly around a shared center of mass. This wobble is incredibly small, almost imperceptible, but it is definitely real. As the star subtly shifts back and forth, its light also experiences a slight change, being momentarily squeezed and stretched by this motion. This phenomenon is known as the Doppler effect. Astronomers can detect these minute changes by using a technique called spectroscopy. This involves breaking down the starlight into its individual component colors and carefully looking for the subtle signatures of motion, small shifts in the spectral lines. This method is called the radial velocity method, and it was actually how the very first exoplanets were initially discovered. This technique works particularly well for massive planets that orbit very close to their stars, such as the hot Jupiters we discussed earlier. However, it has also been instrumental in helping us discover systems with multiple planets and worlds with long, extended orbital periods. We're not actually seeing these planets directly with this method. Instead, we're observing their stars swaying gently under the planet's gravitational influence. It's like watching a cosmic dance that's too distant for us to see the dancers themselves, but close enough for us to feel the rhythm and movement in the subtle music of the starlight. Some exoplanets appear to have their atmospheres escaping into space. A planet's atmosphere is never truly static. Winds blow, clouds drift, and over vast timescales, tiny particles can gradually escape into the vacuum of space. But in some extreme cases, the entire upper atmosphere of a planet may be actively drifting away, slowly leaking into space like a breath dissipating into the void. This process is especially common for hot gas giants that orbit very close to their stars. The intense radiation emanating from the nearby star can superheat the planet's outer atmospheric layers, causing the gases to expand and accelerate until they reach what's called escape velocity, breaking free from the planet's gravity. These planets can develop long, distinctive comet-like tails composed of escaping hydrogen and helium. We've actually observed this phenomenon in several exoplanets, where studies using ultraviolet light clearly reveal these trails of gas streaming out behind them. Over long periods, some planets might lose a significant portion of their mass through this atmospheric escape. Others could potentially be stripped down almost entirely, leaving behind only their rocky cores. This continuous process of atmospheric erosion plays a crucial role in shaping the evolution of planetary systems. It vividly demonstrates how stars, through their powerful radiation and stellar winds, can sculpt, reshape, or even ultimately destroy their orbiting planets. It's a powerful reminder that even vast worlds can undergo profound changes, slowly erode, and eventually fade away, sometimes leaving only their gravitational presence behind as a subtle echo of what once was. We've found planets in star systems with 3 or even more suns. Not every star system is organized like our own, with a single star. Some parts of the galaxy contain not 1, but 2, 3, or even more stars all orbiting each other. And remarkably, within a few of these incredibly complex stellar systems, we have actually discovered planets. Try to imagine a world where the sky is never truly dark, where shadows stretch in multiple directions simultaneously, and where one sun might be rising just as another is setting. These planets must follow incredibly delicate and stable orbital paths to successfully navigate the tangled gravitational pull of multiple stars. Some of them orbit very closely around a pair of stars, much like the circumlunar planets we discussed earlier. Others orbit much farther out, encompassing the entire cluster of stars, tracing wide, sweeping loops around a chaotic gravitational center. The lighting on such worlds would be incredibly strange and dynamic. Seasons would be highly unpredictable, constantly changing with the relative positions of the multiple suns. The night sky, if there truly is one, would be a spectacle of constant motion and multiple points of light. Yet, these planets demonstrably exist. They serve as a powerful reminder that planetary systems can form and persist in ways we never initially expected, even in environments where gravity is incredibly complicated and the night sky never truly settles into a predictable pattern. Despite the odds, planets somehow manage to find a way to exist in these complex, multi-star environments. Some worlds actually orbit the collapsed remains of dead stars. Stars, much like living organisms, do not last forever. They eventually reach the end of their life cycles. Some, like our Sun, will end their lives as white dwarfs, small, incredibly dense remnants of what was once a star. Others, much more massive stars, collapse into incredibly dense neutron stars, or even into the ultimate gravitational traps, black holes. And astonishingly, around some of these stellar corpses, we have discovered planets. These worlds continue to orbit what is left after a star has died. They circle glowing embers, or perhaps pulsing remnants of immense stellar fury. In some cases sometimes, these planets are true survivors, somehow managing to endure the immense chaos of a supernova explosion, a stellar death on an unimaginable scale. In other instances, they might have actually formed later, coalescing from the scattered debris left behind after such a catastrophic event, essentially rising into something new from the cosmic ashes. The light emanating from these dead stars is often dim, perhaps cold, or even strangely distorted. Yet the planets persist, silently tracing their paths through what feels like a vast, celestial graveyard. Some of these worlds are constantly blasted by residual radiation from the dead star, while others drift quietly, circling their defunct suns in a state of eternal twilight. It's a truly haunting and strangely beautiful concept, a powerful reminder that even after the dramatic end of a star, something new and incredibly strange can still begin again, continuing the cosmic story. Now, usually, planets orbit their stars in the same direction that the star itself spins. This is the common way solar systems are thought to form, starting from a large, swirling disk of gas and dust. But nature, as it often does, doesn't always stick to the straightforward rules. We've actually found at least one exoplanet, called YSP-17b, that orbits its star in the completely opposite direction. Instead of moving along with the star's rotation, it's essentially pushing against it. This kind of backwards orbit probably didn't happen smoothly. It's more likely the result of some profound chaos in the system's past, perhaps a near collision with another massive body, a powerful gravitational shove from a distant star, or some kind of violent, large-scale rearrangement that occurred billions of years ago. YSP-17b itself is a massive gas giant, quite bloated and blisteringly hot, and it orbits incredibly close to its star, completing a full loop every few days. The very fact that it moves in reverse, against the natural flow, fundamentally challenges our current understanding of how planetary systems typically evolve over time. It offers compelling proof that the universe is far more flexible, chaotic, and surprising than any single theory we might construct. Some planets simply follow the general flow, going with the cosmic current. Others actively push against it, and some, like MyS P17b, move through the vastness of space with a quiet, persistent defiance, charting their own unique and unexpected course. It might seem impossible, but we've actually detected signs of clouds on planets that are light years away from us. We're not seeing them directly, of course, but by carefully studying the way starlight behaves as it passes through a planet's atmosphere during a transit. As the light from a distant star filters through the very edge of an alien world's atmosphere, certain wavelengths of that light are absorbed, while others pass through or are scattered in different directions. This creates a kind of delicate fingerprint in the light, a unique signature that tells us a great deal about the gases, molecules, and tiny particles suspended in that distant air. In several instances, the data we've collected strongly suggests the presence of clouds. These aren't necessarily the soft, white, cottony clouds we see drifting across Earth's sky. Instead, they might be dark, metallic, or mineral-based clouds, perhaps made from silicates or iron, or even more exotic chemical compounds that we don't fully understand yet. These unusual clouds could reflect or block starlight in peculiar ways, influencing the planet's overall appearance and its temperature. Some planets seem to be permanently wrapped in a cloud cover, while others show changing patterns across their skies, much like weather systems here. We still can't visually see these worlds in detail, but we can, in a remarkable way, read their weather just by analyzing the starlight that passes through them. A whisper of atmosphere from a world far, far away. Consider this: some exoplanets actually orbit much closer to their stars than even Mercury, our own Sun's closest planet. Mercury is already an incredibly hot world, constantly bathed in intense sunlight and having most of its original atmosphere stripped away by solar winds. But some exoplanets exist in even more extreme proximity to their stars, orbiting at distances where no planet in our solar system could possibly survive. These worlds complete their entire orbits in mere hours or just a few days. Their surfaces are likely molten, continuously heated to extreme temperatures, and their atmospheres are constantly whipped away by powerful stellar winds. Many of these super close planets are tidally locked, meaning one side endures blistering, unending daylight while the other remains perpetually frozen in eternal darkness. Others are so close that they actually bulge due to intense tidal forces, stretched and distorted like massive teardrops by the star's immense gravity. These extreme planets fundamentally challenge our traditional ideas of what makes a world habitable. Yet, they are among the easiest to detect because of their incredibly short orbital periods, which allows us to observe multiple transits in a relatively short time. Many of the very first exoplanets discovered fell into this category. They are typically hot, fast-moving, and often quite unstable, but they clearly show us just how incredibly flexible and extreme planetary systems can truly be. Now, at the other end of the spectrum, some planets drift far beyond the reach of any significant sunlight. Not every planet huddles close to its star, basking in its warmth. Some orbit so incredibly far away that the light from their sun becomes nothing more than a faint, feeble glow, a distant pinprick in the blackness. These incredibly distant worlds can take hundreds or even thousands of years to complete just a single orbit around their parent star. In such regions, temperatures plummet to unimaginable lows. Seasons, if they even exist in any meaningful way, would span multiple human generations, and chemical reactions would slow to an almost imperceptible crawl in the deepest cold. Yet, even in these desolate reaches, planets persist, silent and slow, quietly circling their stars at the very outermost limits of gravity's influence. Some might be colossal icy giants, wrapped in thick, frozen clouds of exotic compounds. Others could be barren and rocky, their surfaces crusted over with thick layers of ice and carbon dust. And remarkably, some might even possess hidden warmth deep beneath their surfaces, sustained by the slow decay of radioactive elements within their cores, or perhaps by ancient, residual heat trapped from their very formation. These far-flung orbits are, as you might imagine, extremely challenging to detect, but their confirmed existence serves as a powerful reminder that planets can absolutely survive in places we once thought were utterly empty and lifeless. Even in the loneliest, coldest stretches of space, a world can quietly endure, holding on to its secrets. Imagine Saturn's rings. They are truly beautiful. Delicate bands of ice and dust gracefully suspended around that majestic gas giant. But they might not be the most impressive ring systems in the entire universe. Some exoplanets are thought to possess rings that are thousands of times larger than Saturn's, stretching across truly vast distances. Wide enough, in fact, to potentially eclipse their host stars entirely from our perspective. One fascinating candidate for this is JO Fluo 7b, which is either a giant planet or a brown dwarf, a failed star. It's believed to be surrounded by a ring system that's more than 200 times larger than anything we see around Saturn. These colossal rings could be made of a variety of materials: ice, rock, or dust. Perhaps the leftover remnants of forming moons that never quite coalesced. As this planet orbits, its enormous rings could cast deep, shifting shadows on its star. These shadows would create very unusual and dramatic dips in the star's light, which we can detect even from Earth. If such a planet, with its immense rings, were somehow placed into our own solar system, its rings would stretch so far across the night sky that they would be a truly spectacular sight, easily visible from Earth, dominating our view. These ring systems are, for now, largely hypothetical, but their shadowy presence, inferred from the subtle changes in starlight, hints at an incredible grandeur that is still waiting to be definitively confirmed. We truly have only just begun to scratch the surface of what's out there. For all the incredible things we've learned about exoplanets so far, it's important to remember that we are still very much at the beginning of this journey. The very first confirmed discovery of a planet outside our solar system was made in 1992. In the grand scheme of cosmic time, that was barely a heartbeat ago. Since then, our technology has made enormous leaps forward. Thousands of planets have been found, and many thousands more are currently awaiting confirmation through further observations. We've managed to detect the presence of atmospheres, accurately measure their sizes and orbital periods, and even begin to map the general characteristics of their skies, using subtle changes in light and shadow. However, despite these achievements, we've barely started to truly understand what these distant worlds are actually like. We can't yet see their surfaces in detail. We certainly don't know what they might smell like, what sounds might echo across their landscapes, or what it would feel like to stand on their ground. We can't definitively say which ones have clouds, or continents, or oceans, or most importantly, creatures. The honest truth is that every new exoplanet we discover is like opening a doorway to something entirely new, something we've never encountered or even fully imagined before. And as our scientific tools become ever sharper and more precise, the picture of the universe will only grow stranger, richer, and even more filled with profound wonder. The cosmos is teeming with planets, and we've truly only just knocked on the door of understanding them. For some exoplanets, being incredibly close to a star isn't just about intense heat, it's a destructive force. These planets orbit so incredibly near their suns that the intense radiation and powerful stellar winds begin to actively strip them apart. The outer layers of their atmospheres heat up, expand dramatically, and then gradually evaporate into the surrounding space. Some of these planets actually form long, glowing tails of gas that stretch out behind them, much like comets, as if they are caught in an eternal, slow-motion retreat from their star. Over vast stretches of time, these worlds steadily lose mass, slowly shrinking, becoming thinner, or even transforming entirely. One such planet, named K255554AB, is thought to be literally crumbling under this kind of relentless erosion. Its surface is believed to be shedding dust and debris with every single orbit it completes. It's like observing a planet slowly dissolving before our very eyes, albeit in super slow motion. These aren't just static places to live. They are incredibly dynamic systems, constantly being reshaped and sculpted by their surrounding environment. It's a powerful reminder that even something as vast and seemingly solid as a planet can be worn away, little by little, by the unrelenting light and energy of a star, eventually fading into nothingness. Every time we think we've started to grasp the rules of planets, the universe inevitably presents us with something we simply cannot explain. We've discovered worlds where the skies shimmer with vaporized metal, where the clouds are made of exotic minerals. We've found rocky planets that are hotter than flowing lava and colossal gas, giants that are colder than the deepest reaches of interstellar space. We've seen worlds with dramatically tilted orbits, or ones that spin completely backwards, and some even have ring systems so immense they could easily block out their host star. Some planets we've found seem far too dense for their size, while others are impossibly fluffy and light. Some, by all our current models, shouldn't even exist at all, but they do. Each of these strange discoveries forces us to completely rethink our ideas about how planets form, how they evolve over billions of years, and what the true range of possibilities might be in the cosmos. Science truly thrives on these kinds of surprises. In the vast, swirling chaos of the cosmos, order is only one part of the unfolding story. The rest is comprised of exceptions, unique edge cases, and quiet contradictions. Little cosmic puzzles scattered throughout space, patiently waiting for someone to notice them and begin to wonder. Some exoplanets might truly be water worlds, with absolutely no landmass whatsoever. Imagine a planet where there are no continents, no islands, no shorelines to be found anywhere, just an endless, global ocean stretching out in every direction. These are the theoretical water worlds, exoplanets where the entire surface is completely submerged under liquid water. And we're not talking about shallow seas like Earth's. These oceans could be hundreds or even thousands of miles deep. Beneath the surface, the pressure would be almost unfathomably intense, enough to compress water into those exotic, high-pressure ices we discussed, and even to crush rock into unfamiliar, incredibly dense forms. Some of these worlds might have atmospheres that are incredibly rich in steam, or perhaps thick clouds of vapor perpetually circling overhead. Others could be enveloped in hazy mists, warmed either by the distant starlight or by internal heat sources deep within the planet. If life were to exist on such planets, it would necessarily have to evolve within a deep, perhaps sunless, marine environment shaped more by powerful currents and complex chemistry rather than by direct light. While we haven't definitively confirmed the existence of one of these true water worlds yet, the evidence and theoretical models are increasingly pointing to their possibility. If Earth represents one kind of habitable world, then perhaps these dark, deep oceans represent an entirely different, yet equally viable, kind of environment for life. We've found many mini Neptunes, planets that are small but still swollen with gas. Not every planet fits neatly into the categories we're most familiar with, like rocky planets or gas giants. Between the size of Earth and the ice giant Neptune lies a very curious and increasingly common group of worlds called mini Neptunes. They are larger than Earth, but distinctly smaller than our solar system's ice giants. And crucially, many of them are wrapped in thick, extensive layers of gas. These planets are thought to have rocky or icy cores at their centers, which are then surrounded by substantial envelopes of lighter gases, primarily hydrogen, helium, and other volatile compounds. From a distance, they might appear somewhat similar to Neptune, perhaps with a blue or greenish hue. However, their internal structures and compositions could be wildly different. Some might possess deep, boiling oceans beneath their gaseous clouds, where water could exist in a super-critical state. Others might have no discernible solid surface at all, simply transitioning from a very dense gas to a liquid. They're too small to be classified as true gas giants, but definitely too large to be considered simply rocky super-Earths. For a long time, scientists weren't even sure if planets like this could exist, as our own solar system doesn't have a direct analog. Now, we know they are remarkably common, possibly even the most prevalent type of planet found across the galaxy. They are strange, often swollen, and still quite mysterious, filling in a vast conceptual space between what we initially expected planetary types to be. Some planets are so puffed up they're like cosmic balloons. Certain exoplanets are so incredibly inflated that they appear much lighter than their actual size suggests. These are often referred to as puffy planets. They possess a very large diameter, but have an unusually low density. Imagine huge, soft worlds that, if you could somehow find a bathtub the size of a star, would actually float on water. One well-known example is BioS P17b, which we discussed earlier for its retrograde orbit. This gas giant is about twice the size of Jupiter, but has only a fraction of its mass. These puffy planets likely formed much farther away from their stars, in the colder, outer regions of their systems, and then later migrated inward. Now, the intense heat radiating from their nearby star causes their atmospheres to swell and expand dramatically. The powerful radiation from the star might also be breaking apart molecules within their atmospheres, contributing to the planet's strange, low-density properties. Some puffy planets have visible tails of escaping gas, further indicating their unusual atmospheric dynamics. Others simply seem impossibly light for their enormous size. We still don't fully understand all the mechanisms behind their existence, but they clearly demonstrate how incredibly elastic and dynamic a planet's structure can be. They're not rigid and fixed, but rather soft, somewhat unstable, and stretched by the relentless light and energy of their host star. On some exoplanets, a single day can actually be longer than its entire year. On Earth, our day, the time it takes for one rotation on our axis, is about 24 hours. Our year, the time it takes to orbit the Sun, is 365 days. These are very different timescales. But for some exoplanets, particularly those that orbit extremely close to their stars, this distinction blurs significantly. In certain cases, the time it takes for the planet to complete one full rotation on its axis is actually longer than the time it takes for it to complete an entire orbit around its star. This means the planet finishes its journey around its Sun before it even completes a single full turn on its own axis. These planets are almost always tidally locked, with one side perpetually facing their Sun. The night side remains in eternal darkness, frozen and still, while the day side burns under unending, ceaseless daylight. There's no sunrise or sunset on such a world, just one face forever turned towards the light, and the other forever turned away. On a world like this, the very idea of time itself begins to blur. A day that never truly ends, a year that races by in comparison, and a sky that is forever divided into two distinct, unchanging halves of light and dark. It offers a profoundly different experience of celestial mechanics. Some worlds might be permanently covered in thick, hazy skies. We often picture alien worlds with clear, pristine skies offering stunning views of distant stars. But some exoplanets might be perpetually wrapped in dense, thick layers of haze, effectively blocking out most of the incoming light and obscuring everything that lies beneath. These hazes can be composed of complex hydrocarbons, acting like a photochemical smog, or perhaps exotic clouds made of unfamiliar chemical compounds. Here on Earth, we see a similar effect with Saturn's moon Titan, which is famously shrouded in a golden, opaque fog that completely hides its surface from view. On exoplanets, especially those orbiting cooler, dimmer stars, ultraviolet light can trigger strange and complex chemical reactions in the upper atmosphere. This leads to the gradual build-up of thick, murky layers that effectively trap heat and scatter light in unusual ways. From space, these planets might appear rather dull or muted, their colors softened and obscured by the persistent haze. But deep beneath these perpetual clouds, vast oceans might churn, powerful winds might scream, and entirely alien landscapes could be waiting in silence. We can't see them clearly yet, not with our current technology. But we know the haze is there, a mysterious veil drawn over distant, hidden worlds, hinting at what lies beneath. We've actually seen evidence of winds whipping across exoplanets at thousands of miles per hour. Weather isn't just a phenomenon unique to Earth. On many exoplanets, especially the large gas giants, atmospheric winds can reach absolutely extraordinary speeds, far surpassing anything ever observed in our own solar system. Some exoplanets, particularly those that are tidally locked with one side, always facing their star, experience immense and permanent heat differences. This creates incredibly powerful thermal gradients that, in turn, drive ferocious winds across the planet's atmosphere. Using advanced space telescopes, astronomers have successfully detected signs of these winds blowing at speeds of up to 50,000 miles per hour. That's fast enough to traverse the entire width of the United States in less than an hour. These incredible winds can dramatically shift clouds, completely reshape the planet's heat distribution patterns, and even carry vaporized metals across the entire world. In some cases, these powerful winds even redistribute the light itself, causing the brightest part of the planet to be shifted away from the precise point where the star's light hits directly. This movement is invisible to the naked eye, but it's clearly written into the subtle glow of the planet's light, a powerful whisper of motion emanating from a far-away sky. Some planets could be tidally heated from the inside, independent of their star. Not all planetary warmth comes solely from a nearby star. Some exoplanets, especially those that follow highly eccentric, stretched-out orbits, might be heated intensely from the inside out, thanks to powerful tidal forces. As these planets move through varying gravitational pulls from their star or from neighboring planets, their interiors are constantly stretched and flexed, much like squeezing a rubber ball. This continuous internal friction generates significant warmth deep beneath the surface. This is the very same mechanism that keeps Jupiter's moon, Io, incredibly volcanically active, making it the most volcanically active body in our solar system. On exoplanets, this kind of tidal heating could be so intense that it melts rock into magma, creating vast subsurface oceans of molten material. Or it could keep subsurface oceans of liquid water or other compounds in a liquid state, even beneath incredibly thick shells of ice, deep within planets that otherwise appear cold and dark on the outside. These planets might look frozen and lifeless from an external perspective, but deep inside, they are alive with dynamic motion and heat, even without direct sunlight. It's a powerful reminder that energy can originate from within a world, and that even in the frigid outer reaches of a star system, a planet may still harbor significant internal warmth and geological activity. We've discovered planets that exist in incredibly ancient star systems. Some stars are almost as old as the entire universe itself, having formed in the galaxy's earliest chapters, billions of years ago. And remarkably, orbiting a few of these ancient, venerable stars, we have found planets. These worlds have been quietly circling their suns for billions of years, a timescale far longer than Earth has even existed. One compelling example is the star system Kepler 444, which is estimated to be over 11 billion years old. This system hosts 5 small, rocky planets. These worlds originate from a time when the universe had far fewer heavy elements available, suggesting they may have formed from very different initial materials than Earth did. What might such ancient planets be like? Could their surfaces be worn incredibly smooth by eons of impacts and geological processes? Could they have once supported life, perhaps billions of years before life even began to emerge here on Earth? We may never know the full answers, but these ancient systems offer a profound reminder of just how long planets can persist. They survive stellar storms, the slow, relentless tug of galactic tides, and the immense, quiet march of time itself. They are truly cosmic elders, silently circling in the deep past, still here, still turning, holding untold histories within their ancient cores. Some exoplanets may have moons that we are yet to find. Where there are planets, it's a very logical assumption that there may also be moons. And yet, for all the thousands of exoplanets we've discovered and confirmed exomoons, moons orbiting planets outside our solar system remain incredibly elusive. They are inherently difficult to detect, being very small and subtle, often hidden within the observational noise from their much larger parent planets. However, we have observed tantalizing hints. Tiny variations in a planet's transit across its star, subtle wobbles in timing, or small dips in brightness that don't quite fit the expected model for a single planet. One strong candidate, a possible moon orbiting the gas giant Kepler 1625b, is currently undergoing intensive study. If confirmed, this exomoon would be absolutely enormous, larger than any moon in our own solar system, but even smaller exomoons could be incredibly significant. They might play a crucial role in stabilizing planetary climates, much like our moon helps stabilize Earth's axial tilt. They could also shape powerful tides, or even provide sheltered environments, where life could potentially emerge and thrive. Some exomoons might possess subsurface oceans, similar to Jupiter's moon Europa or Saturn's moon Enceladus, where liquid water is protected by an icy shell. Others might be rocky and heavily cratered, silently drifting in a perpetual twilight above their colossal gas giants. We haven't seen them clearly yet, but it's highly probable they are out there, quietly circling, patiently waiting to be discovered. It's also highly probable that some massive exoplanets could have entire moon systems of their own. Just as planets orbit stars, moons orbit planets. I'm for truly massive exoplanets, especially the large gas giants. It's incredibly likely that they host entire systems of moons, forming miniature solar systems of their own. In our own solar system, for instance, Jupiter and Saturn each boast over 80 known moons, ranging in size from tiny captured asteroids to massive worlds that are larger than planets like Mercury, some even possessing subsurface oceans. Now, try to imagine a gas giant many times more massive than Jupiter, orbiting a distant star. It could easily possess dozens, perhaps even hundreds, of moons, each with its own unique characteristics. Some of these moons might be rocky and heavily cratered, scarred by impacts. Others could be wrapped in thick icy shells, or possess their own substantial atmospheres. A few might even orbit within the habitable zone of their parent planet, potentially shielded from harsh stellar radiation and warmed by the very tidal forces we just discussed. We haven't definitively confirmed any of these complex exomoon systems yet, but the potential is truly staggering. It's not just about finding individual planets, but entire families of worlds, drifting together, locked in a delicate gravitational harmony, far from our familiar home. Some exoplanets might actually support life, but in forms we could barely recognize. When we tend to imagine alien life, our minds often default to picturing conditions similar to those on Earth: blue skies, abundant liquid water, and a comfortable temperature range. However, life might not necessarily require any of these specific conditions. Some exoplanets could host living organisms in environments wildly different from our own. Imagine life thriving in highly acidic clouds, or deep beneath ice, covered oceans, or within high-pressure atmospheres thick with methane. It's even conceivable that life could exist that doesn't rely on water, or carbon, or even DNA as its fundamental building blocks. Here on Earth, we already have extremophiles, organisms that live in incredibly harsh environments, such as boiling acid pools, radioactive caves, or near volcanic vents deep in the ocean where no sunlight ever reaches. So on distant planets, it's entirely possible that life could take on even stranger, more resilient forms. We might not be looking for walking, talking creatures, but rather microbial networks, complex chemical colonies, or self-replicating systems that flourish in environments we would find instantly deadly. We may never personally encounter them in a direct way, but if we listen incredibly closely, analyzing the light and shadow from alien worlds, we might someday detect the first faint signature: a peculiar chemical imbalance in the atmosphere, a subtle breath of something truly living. We've found planets that barely skim the edge of being stars themselves. There's a somewhat blurry line between what we define as a planet and what we call a star. And some exoplanets exist right at this fascinating boundary. These are truly giant objects, often referred to as brown dwarfs, or super Jupiters. They are massive enough to initiate a very limited amount of nuclear fusion in their cores, specifically fusing deuterium, a heavier isotope of hydrogen. However, they are not massive enough to sustain the continuous, powerful fusion reactions that truly power full-fledged stars like our Sun. They glow faintly, primarily from the residual heat left over from their formation, and some can even emit detectable infrared radiation. One such object, called HD 10546b, is so incredibly large and hot that it might actually straddle this boundary between being a planet and a failed star. Scientists are still actively debating precisely where the cutoff lies. How massive can a celestial body become before it transcends the definition of a planet and becomes something else entirely? These between worlds might form in ways similar to planets, accreting from a disk of material, or they might form more like stars through the direct collapse of a gas cloud. We don't always know which process applies, but they serve as a powerful reminder that categories in space are often fluid and blurry. The cosmos is filled with these shimmering, shifting edges, where one type of object gradually transitions and slowly becomes another. Some worlds exist right on the very edge of the habitable zone around their star. The habitable zone is often affectionately called the Goldilocks zone. This is the range of distances around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, where water would boil away, and not too cold, where it would freeze solid. It's the just right spot. Earth, of course, comfortably resides within our Sun's habitable zone, and a growing number of exoplanets have been found within these zones around their own stars. They orbit at precisely the right distance for water to potentially remain stable in liquid form, which is considered one of the most crucial ingredients for life as we currently understand it. However, simply being located in the Goldilocks zone doesn't automatically guarantee habitability. A planet's atmosphere, its rate of rotation, and its specific surface conditions all play vital roles in determining whether life can actually thrive there. On planets situated right on the very boundary of this zone, conditions become much more complex and uncertain. If it's too far out, water might predominantly freeze. If it's too close in, it might boil away. But right on the edge, things are more nuanced. A very thick atmosphere, for example, could help trap heat and keep a planet warm. Conversely, a high reflectivity might help keep a planet cool. And dramatic seasonal shifts or an eccentric, oval-shaped orbit could cause significant, dramatic climate swings, making one hemisphere habitable while the other remains too cold or too hot for extended periods. Life, if it were to exist on such worlds, might only be found in isolated pockets, perhaps deep beneath thick ice sheets, or within extensive cave systems, or clustered around volcanic vents that provide internal warmth. These edge worlds are neither entirely comfortable nor completely barren. They are places of inherent tension and profound potential, where the delicate balance between warmth and cold, light and dark, could tip dramatically either way, or hold on, just barely, in a precarious equilibrium. They challenge our definitions of what makes a place suitable for life. We are actively learning to study the intricate chemistry of alien atmospheres. Until very recently, the idea of accurately analyzing the atmosphere of a planet located light years away seemed utterly impossible, a distant dream. But now, thanks to incredibly precise and powerful instruments, like the James Webb Space Telescope, we are actually beginning to do exactly that. When an exoplanet passes directly in front of its star. Some of the starlight actually filters through the planet's atmosphere before reaching our telescopes. That filtered light carries subtle, yet distinct, chemical fingerprints, specific spectral lines that correspond to the molecules present in the air. By meticulously breaking this light apart and analyzing those spectral lines, scientists can now detect the presence of water vapor, carbon dioxide, methane, and many other compounds. From this information, we can start to infer things about the presence of clouds, the atmospheric pressure, and even the approximate temperature of these distant worlds. In some truly exciting cases, we may even be able to spot what are known as biosignatures, subtle chemical hints that strongly suggest life might be actively influencing the atmosphere. It's like deciphering a complex message sent from across the vast expanse of the galaxy, a message cleverly hidden within the colors and patterns of starlight. We are still in the very early stages of this groundbreaking work, but with each new spectrum we obtain, we get a little bit closer to truly understanding what alien skies are actually made of. Molecule by molecule, some exoplanets may experience seasons that stretch on for decades. On Earth, our seasons are primarily defined by the slight tilt of our planet's axis as it orbits the Sun. This gentle, lean changes the angle at which sunlight hits different parts of the planet throughout the year. But on some exoplanets, the mechanics that drive seasons are far more extreme. A much larger axial tilt, a highly stretched or elliptical orbit, or even the presence of multiple stars can create incredibly wild and prolonged seasonal effects. Imagine summers that last for decades, or winters that span entire human lifetimes. A planet might swing incredibly close to its star, warming dramatically and experiencing an intense summer, only to then drift far, far away into a deep, frozen hibernation for years or centuries. Other planets might have truly chaotic seasons, shifting unpredictably with almost every orbit due to complex gravitational interactions. Long, extended summers could allow life to briefly bloom and flourish, only for it to then vanish or go dormant beneath decades of intense cold. Or, entire generations of organisms might live and die within the span of a single protracted spring. The very rhythm of life, if it exists on such worlds, would have to follow an entirely different kind of calendar, one written not in our familiar days or years, but in slow, sweeping arcs and intricate stellar dances. On these worlds, time itself seems to move differently, and consequently, so might everything else that exists upon them. Conversely, others might experience a state of eternal twilight. Some exoplanets could perpetually exist in a state of between, a place where full daylight never truly breaks, and complete darkness never entirely falls. This can happen on tidally locked planets, where, as we discussed, one side always faces its star, while the other is in permanent night. But precisely between these two extremes lies a thin, transitional region often called the terminator, a continuous ring of perpetual twilight. Here, the sky might glow dimly and softly forever, caught in an unending balance between the burning light of the star and the deep, silent dark in this terminator zone. The temperature could be significantly more stable, and the winds might be more moderate than on the extreme day or night sides. If life were to exist on such a world, it might flourish specifically along this twilight boundary, a narrow band of gentle shadows and muted warmth. There would be no dramatic sunrise, no breathtaking sunset, just a soft, slanted glow from a star that remains perpetually fixed at the edge of the sky. Imagine a planet with a horizon that never actually moves, a place where time drifts in a constant half-light, and nothing ever truly experiences the full cycle of day and night. It's a profound thought about the stillness of existence. We've discovered planets that are locked in intricate orbital resonance with each other. In some star systems, planets don't simply orbit independently in their own separate paths. Instead, they move together in a quiet, synchronized dance. These arrangements are known as orbital resonances, where the timing of their orbits aligns in precise, whole number ratios. For example, for every 2 orbits one planet completes around its star, another planet in the same system might complete exactly 3 orbits. This kind of gravitational balance helps prevent them from colliding with one another and significantly stabilizes their long-term motion. We've actually observed similar phenomena right here in our own solar system, particularly among Jupiter's larger moons. But we've also found exoplanetary systems that exhibit long, complex chains of resonance involving 3, 4, or even more planets. It's truly like a cosmic symphony, with each world playing its own unique rhythm, yet always remaining in perfect harmony with its neighbors. These arrangements are incredibly delicate. Even a small change in gravity or motion could potentially throw the entire system out of balance. But instead, they hold together gently and beautifully, orbit after orbit, for billions of years. The universe, it appears, is not solely characterized by chaos and randomness. It also possesses a deeply musical and ordered side, expressed through these precise gravitational ballads. Not everything we observe in space makes immediate sense. Some exoplanets display mysterious signals that we still don't fully understand. For instance, some exoplanets show light curves, measurements of how their star's brightness changes over time, that fluctuate in unexpected ways, dimming and brightening in patterns that don't quite match our simplest models. Others appear to have complex ring systems, or unusual clouds, or orbiting debris that casts irregular, shifting shadows. One famous example is a star nicknamed Tabby's star, which dimmed and brightened in very strange, uneven patterns that sparked intense global curiosity. Some scientists theorized it might be a massive swarm of comets, while others, more speculatively, even imagined vast artificial megastructures built by an alien civilization. Although there's no actual evidence to support that particular idea, still, the fundamental mystery persists. Light curves often wiggle and wobble in peculiar ways. Transit patterns can shift slightly over time. Some planets show additional, unexplained dips in brightness either before or after they pass in front of their stars. Others seem to change shape, almost as if they are wrapped in swirling clouds or trailing plumes of dust. We are actively working to decode these complex patterns and unravel their meaning. But for now, they remain unanswered questions, gentle flickers of something we don't yet fully comprehend, yet are completely captivated by. They are cosmic puzzles, silently waiting for us to unravel their secrets. There are planets with orbits so wild and elongated that they almost escape their stars entirely. Most planets move in fairly quiet, regular, and somewhat circular loops around their stars. But some exoplanets follow incredibly long, stretched out orbits, so elliptical that they swing incredibly far from their host stars before eventually plunging back in. Much like cosmic comets on immense timescales, these extreme orbits can last for hundreds of years. At their farthest point, the planet might receive almost no light or warmth from its distant sun, plunging into a deep, frigid darkness. Then, at their closest approach, they race past their star, pulled by intense gravity, heated in brief, blinding flashes of light and radiation. These journeys are often violent, inherently unstable, and frequently temporary in cosmic terms. Some planets might have been flung into these highly eccentric orbits by powerful collisions with other celestial bodies, or by the close flyby of a passing star. Others might, one day, be lost entirely, accumulating enough velocity to escape their star system and drift alone into the vastness of interstellar space, becoming rogue planets. They are like cosmic exiles, barely bound by gravity's grip, dancing precariously on the very edge of freedom. Their paths are unpredictable, their long-term futures uncertain, but still they persist in their immense, dramatic orbits. Each pass by their star is a powerful reminder of just how dynamic and dramatic the life of a planet can truly be. Some exoplanets actually orbit burnt-out stellar corpses called white dwarfs. After a star like our Sun reaches the end of its life, it sheds its outer layers and leaves behind a white dwarf. A small, incredibly dense, glowing ember of what it once was. These remnant stars no longer fuse hydrogen in their cores, so they don't shine with the same energy and brilliance of their youth. However, they remain incredibly hot and bright for billions of years. And remarkably, around some of these stellar remnants, we have discovered planets. Some of these planets orbit very close to the white dwarf, having somehow survived unimaginable changes as their star first ballooned into a red giant and then dramatically collapsed. Others might have formed later, coalescing from the leftover debris that surrounded the dying star. The environment around a white dwarf is extreme. While the light is dim, radiation can still be intense, and the gravity near the white dwarf's surface is crushing. But even here, planets persist. Some may even lie within a narrow band around the white dwarf, where temperatures are just right for liquid water to exist, warmed by the star's cooling embers. These planets are orbiting the dead, but they are not dead themselves. They are survivors, echoes of a previous era, powerful proof that even in the aftermath of stellar death, the enduring story of planets may continue, unfolding in unexpected ways. It's also possible that some planets have formed directly from the remains of destroyed worlds. In the incredibly chaotic early stages of a young solar system, collisions are a very common occurrence. Planets can be shattered, moons can be violently torn apart, and vast amounts of debris can be scattered across space. Sometimes, from this very wreckage, new worlds can begin to form, built entirely from the fragmented remnants of earlier, larger bodies. We've seen tantalizing hints of this process in the dusty disks surrounding some young stars, where ring-shaped gaps or unusual structures suggest ongoing collisions or the active construction of new planets from shattered pieces. Some exoplanets might actually be the stripped-down cores of what were once much larger planets, their atmospheres having been blasted away by ancient impacts or intense stellar activity. Others could be aggregates, essentially collections of fragments that have been slowly fused together by gravity and time. These are, in a sense, recycled worlds, not born whole and complete, but rather meticulously rebuilt from the pieces of something else. Their surfaces might be rough, heavily scarred, or even still partially molten from the immense energy of their formation. Their orbits might be tilted or highly eccentric, reflecting their violent origins. But they exist, and they serve as a powerful reminder that destruction isn't always the absolute end. Sometimes, it's just the dramatic start of something entirely new, something stranger, perhaps rougher, and ultimately more resilient than what came before. Some planets may have once been part of an entirely different star system. We know that planets form around stars. That's a fundamental principle of astronomy. But over the incredibly long lifespan of a galaxy, stars and their planetary companions don't always remain together in their original configurations. Powerful gravitational encounters, such as close flybys with other stars, or the complex, chaotic dynamics within crowded star clusters, can actually fling planets from one star system into another. It's entirely possible that some exoplanets we observe today began their lives orbiting one star, only to end up gravitationally captured by a completely different one. These interstellar adoptees can often end up on very unusual orbits, perhaps highly tilted or extremely elliptical, or even unstable, slowly decaying over time. We can't always definitively trace their exact origin, but in some cases, their unique chemical signatures or their peculiar orbital motions hint strongly that they don't quite belong to their current host star in the way that naturally formed planets do. They are like cosmic immigrants, pulled from one stellar family into another, survivors of immense stellar drift and sheer gravitational chance. And they serve as a powerful reminder that solar systems are not sealed, isolated units. They are dynamic, they evolve, they can exchange parts, and sometimes they even gather strangers from among the distant stars, adding new, unexpected members to their cosmic families. We've observed exoplanets that could be young versions of what Earth once was. When we look at distant planets through our powerful telescopes, we're not just seeing other worlds as they are now. Sometimes, we're catching glimpses of different versions of our own planet's distant past. Some exoplanets might closely resemble what early Earth was like billions of years ago, when our atmosphere was significantly thicker, perhaps rich with carbon dioxide or methane. It was a time when life, if it existed at all, was just beginning to take its very first tentative hold in a primordial soup. These young planets might still be actively forming continents, building up their atmospheres, or undergoing massive and dramatic geological changes. Intense volcanic activity, complex chemical reactions, and extreme weather events could be shaping their futures, much as they shaped Earth's future billions of years ago. Studying these young Earths could provide invaluable insights into how our own planet came to be the way it is today. What did our skies look like a billion years ago? What gases filled the air? What powerful storms raged over silent, nascent oceans? Some exoplanets may hold the answers, acting as cosmic snapshots of an earlier, more volatile chapter in the story of habitability. They are distant, silent echoes of the Earth, as it was long before we were here to name it or observe it. We've seen giant planets orbiting tiny, dim stars. Not all stars in the universe are large and bright like our Sun. In fact, the vast majority of stars in our galaxy are actually red dwarfs, small, relatively faint, and incredibly long-lived stars. And remarkably, orbiting some of these quiet, unassuming stars, we have discovered enormous planets. At first glance, it seems counterintuitive. How could a tiny star possibly host a giant world, perhaps even a gas giant many times the size of Jupiter? But nature, as always, consistently finds a way to surprise us. In several documented cases, we've detected planets that are the size of Jupiter, or even larger, orbiting stars that are barely a tenth the size of our Sun. These massive planets often reside very close to their diminutive stars, completing their orbits in just a few Earth days. The visual contrast is truly striking, a hulking, colossal planet looming beside a dim ember. Like the temperature within this twilight band, could be more stable, more moderate than the searing heat of the dayside or the crushing cold of the nightside. If life does exist on such a world, it might flourish exclusively along this twilight boundary, a narrow strip of gentle shadows and muted warmth, perfectly adapted to the constant, subdued light. There would be no dramatic sunrise or sunset, just the soft, slanted glow of a star forever locked at the edge of the sky. It's a planet with a horizon that never moves, a place where time drifts in a perpetual half-light, and where nothing ever truly sleeps or completely awakens. We've discovered planets locked in orbital resonance with each other. In some star systems, planets don't simply orbit independently. They move together in an incredibly quiet, precise synchronicity. These are called orbital resonances, where the timing of their orbits aligns in perfect, simple whole number ratios. For example, for every 2 orbits one planet completes, another might complete exactly 3. This delicate balance prevents them from colliding and helps to stabilize their intricate motions over vast cosmic timescales. We've observed this kind of resonant behavior in our own solar system, for instance, among some of Jupiter's moons. But we've also found exoplanetary systems with long, complex chains of resonance, involving 3, 4, or even more planets, all moving in perfect step. It's like observing a cosmic symphony, with each world playing its own distinct rhythm, separate yet always in perfect harmony with its neighbors. These arrangements are incredibly delicate. Even a small change in gravity or motion could throw the entire system out of balance. But instead, they hold together gently, beautifully, orbit after orbit, for billions of years. The universe, it seems, is not solely characterized by chaos. It also possesses a profoundly deep, inherent musicality, a silent, celestial choreography that unfolds with breathtaking precision. Not everything we observe in the cosmos makes immediate sense. Some exoplanets present mysterious signals that we still don't fully understand. Certain exoplanets show light curves that fluctuate in unexpected ways, dimming and brightening in patterns that simply don't match our current, simple models of planetary behavior. Others appear to possess rings, or complex cloud structures, or orbiting debris that casts irregular, puzzling shadows. There's a famous star, nicknamed Tabby's star, that dimmed in strange, uneven patterns, sparking global scientific curiosity and widespread speculation. Some scientists thought it might be caused by a vast swarm of comets, while others, more speculatively, imagined immense artificial structures built by an alien civilization, though no evidence has ever supported that latter idea. Still, the mystery surrounding Tabby's star, and many other similar observations, remains. Light curves continue to wiggle and wobble in perplexing ways. Transit patterns shift unexpectedly. Some planets show additional, unexplained dips in brightness either before or after they pass in front of their stars. Others seem to change shape, as if wrapped in ever-shifting clouds or trailing long streams of dust. We are gradually beginning to decode these complex patterns, slowly piecing together the puzzle. But for now, they largely remain unanswered questions, subtle, gentle flickers of something we don't yet fully comprehend, yet cannot possibly look away from, compelling us to continue our search. There are planets with orbits so wild and stretched out that they nearly escape their stars altogether. Most planets, as we know, move in fairly quiet, regular, circular loops around their suns. But some exoplanets follow incredibly long, stretched out, elliptical orbits, so elongated, in fact, that they swing immensely far from their stars before eventually plunging back in. much like cosmic comets on a grand scale. These extreme orbits can span hundreds of years. At their farthest point, the planet might receive almost no light or warmth from its distant star, existing in near total darkness and profound cold. Then, at their closest approach, they race past their star, pulled by intense gravity, heated in brief, blinding flashes of energy. These journeys are often violent, inherently unstable, and frequently temporary. Some planets may have been flung into these extreme orbits by powerful collisions with other celestial bodies or by the gravitational influence of passing stars. Others might, one day, be lost entirely, gaining enough velocity to escape their star system and drift alone through the vastness of interstellar space, becoming rogue planets. They are essentially cosmic exiles, barely bound, dancing precariously on the very edge of gravity's relentless grip. Their paths are unpredictable, their futures uncertain, but still they persist in their orbits. Each dramatic pass by their star serves as a powerful reminder of just how dynamic and dramatic the life of a planet can truly be, a testament to the powerful forces at play in the cosmos. Some exoplanets orbit burnt out stellar corpses called white dwarfs. After a star like our Sun eventually dies, it leaves behind a white dwarf, a small, incredibly dense, glowing ember of what it once was. These stars no longer undergo nuclear fusion. They don't shine with the vibrant energy of youth. However, they remain intensely hot and bright for billions of years, slowly cooling over immense timescales. And astonishingly, orbiting around some of these stellar remnants, we have found planets. Some of these planets are found incredibly close in, having somehow survived unimaginable changes as their star swelled into a red giant and then dramatically collapsed. Other planets may have formed later, coalescing from the leftover debris that surrounded the dying star. The environment around a white dwarf is extreme. Radiation can be intense, and the gravity near the white dwarf is absolutely crushing. But even here, planets persist. Some may even lie within a narrow, somewhat habitable band where temperatures are just right for liquid water to potentially exist. These planets orbit the dead, but they are not dead themselves. They are incredible survivors, echoes of a past system, and powerful proof that even in the aftermath of stellar death, the enduring story of planets may continue, finding new ways to exist.